Here we go, Chapter 6, problem set number 5. Our first problem is problem number 39. Problem number 39 reads, calculate the ratio of the drag force on a jet flying at 1,000 kilometers per hour at an altitude of 10 kilometers. Okay, so this one here, so the altitude here is 10 kilometers. So we're calculating the ratio to the drag force on a prop-driven transport flying at half the speed and half the altitude. So here the altitude is only equal to 5 kilometers. Now, something that we have a sense of about the atmosphere is that the higher you are, the less dense. And so they gave us these values here. They said, well, look here, you know, the air density at this altitude is 0.38, but the air density at this altitude, so lower altitude, higher air density. In fact, I'm looking at here, and it almost looks to be a linear kind of relationship, but that doesn't actually matter. So let's just figure out what the drag force is. So let's do the drag force. So our drag force, it's equal to 1/2 c rho a v squared, where c is the drag coefficient, rho is the air density, a is the effective cross-sectional area, and v squared is the speed. So it says, assume that the airplanes have the same effective cross-sectional area and same drag coefficient. All right, so let's do, we're going to just do the ratio then. So, okay, drag for the jet divided by drag for the prop. 1/2 c rho a v squared. So this is for the jet, and this is for the jet, and we're going to divide that by 1/2 c rho a v squared, and this for the prop, and this for the prop. Now, what happens here effectively is the halves go away, the c's go away, the a's go away, and we're left with rho v squared over rho v squared. This is for the jet, that's for the jet, and that's for the prop, and that's for the prop. So, to get the ratio, all right, I think we can just plug these things in. So here we have, for the jet, it's 0.38 times the velocity squared divided by the density times the velocity squared. And I think we can just plug and chug that and see what happens. I'll grab my handy dandy calculadora. And I got 2.26. All right, not too bad. Let's move on to the next one. Next one's an all-time classic. It says, a puck of mass 1.5 kilograms slides in a circle of radius r is 20 centimeters on a frictionless table while attached to a hanging cylinder of mass 2.5 kilograms by means of a cord that extends through a hole. What keeps the cylinder, what speed keeps the cylinder at rest? So when I look at this here, if this is spinning fast enough, it's going to hold this thing up. That's what it says. If it slows down, it's going to go this way. So what we're going to do is let's set up some force diagrams for these bad boys. Okay, let's do the puck first, and we're going to do a side view for the puck. So this is little mg, the weight of the puck. It's sitting on a table, so that's the normal force. But it's a frictionless table, so that's nice. And if we're looking at a side view, this is the that's the string pulling in, and we're going to call that T for tension. Let's do the force diagram for this guy, the hanging weight here. Now, if he's at rest, If he's at rest, this is big mg, that's his weight, and if he's at rest, that's T for tension, and those should balance. And so this T and this T are the same. So we look at this one and we say, oh, well, what do we know about the net force? It's equal to 0. Therefore, the tension is equal to big mg. Let's do this one. What do I know about the net force on this one? It's going in a circle, so the net force on this one is mv squared over r. But what do I notice about the net force? The up and downs cancel, so the net force is just the tension. So the tension is equal to little mv squared over r. But what do you notice? The tension is also big mg. So I'm just going to set them equal to each other. I'm up with mv squared over r is equal to big mg. And I think I have enough to plug and chug this one. So it says the mass of the small one is 1.5 kilograms. V squared is what I'm calculating. The R here has to be in meters. They gave us 20 centimeters, so 0.2 meters. And the big M is 2.5 kilograms times our G value, which near the surface of the Earth is 10. Let me get my handy dandy calculator out. Take the square root. I got the speed is equal to 1.83 meters per second. All right. So this one is actually quite challenging. So we're going to have to dig into this one. It may take a couple pages to do, but it says in figure 6.45, that's this, I drew it all for us, a 1.34 kilogram ball is connected by means of two massless strings, each of length L, 1.7 meters. So let's jot down this stuff as it comes out here. So it says that L is equal to 1.7 meters. It says the mass of our ball, the mass of our ball is 1.34 kilograms. The strings are tied to the rod with a separation D, also, interestingly enough, 1.7 meters. Now, what that indicates to me right away is if this is 1.7, 1.7, and 1.7, this is a equilateral triangle. And if I were to split this, then this would be a 30-degree angle here and a 30-degree angle here. I think that's going to be important when we do the geometry for the force diagram. The tension in the upper string is 35 newtons. And they want us to find, so this T up here, okay, we're going to call the tension here, this is TU for upper. We're going to call this one down here, we're going to call it TL for lower. So the tension in the upper string is 35 newtons. Now, that does not indicate that they're the same, because if you think about this, the ball is spinning here, right? This one has to pull down and in, this one has to pull up and in. So they're going to be different forces for sure. So they want to find out what is the tension in the lower string, what is the magnitude of the net unbalanced force on the ball, what is the speed of the ball, and what direction is the F net. All right. So the first thing I want to do is I definitely want to draw a force diagram for this ball. All right, so what are some of the forces on the ball? Well, one thing for sure is the Earth is pulling it down. Oh, that's a little too long. The reason I know it's too long is because if it's a 1.34 kilogram ball, and this is the mg here, it's only going to be 13. And this one's got to be 35. So when I draw this force, right, this pulls on the ball this way. So this is T upper. Now, when I break this up into its component parts, there's an up component and a to the left component. So I mentioned earlier that this is a 30-degree angle, so we're going to see how the geometry works. Now, this one is going to pull down and to the left. So if we just work out just the geometry before we do anything else here. If that's a 30-degree angle, then that's also a 30-degree angle. If this is 35, then this one is 17.5 newtons. It's half of 35 because it's a 30, 60, 90 triangle. Well, we know that this force here is 13.4 newtons. So if I have 17 up and I already have 13 down from the pole, how much more down do I need from this string? I mean, frankly, I know the T lower here is going to pull to the left and down, but the down component only has to be like 4.1 newtons. That's that force right there. So when we look at the forces in the geometry, it actually provides us with some reasonable understanding of what's going on. But I think we have to look at the verticals to really figure out what's going on. So let's do it like this. We'll make the MG blue. We'll make the T lower green. And we'll leave the T upper red. Okay, so let's do the F net statement. So let's talk about the F net in the y direction. Well, this object is spinning around the circle, so the F net in the y direction is actually equal to 0, which is good for us. What are the F nets in the y direction? Well, I have basically this one here, which would be the T upper in the y direction. So I have T upper in the y direction. I'm going to subtract off this one over here, which is the T lower in the y direction, because that's down. And my MG is down. So I can set these equal to 0. T upper in the y direction minus T lower in the y direction minus MG. Now, let's talk about this. Let's talk about this T upper in the y direction. So they give us the tension in the upper is 35. This side over here, relative to this angle, is the opposite side. So I'm going to say that T upper in the y direction is equal to T sine theta, where theta is that 30 degrees because of this geometry here. So if you look, there's 30 there. That would also be 30. That matches this. Those are alternate interior angles. And so if we solve for this, T upper in the y direction is equal to 35 sine theta. So T upper in the y direction. Sine 30, oh, sorry. Sine 30 is a half, so this is 17.5. So this is what I mentioned earlier. That's how I know that's 17.5. So 0 is equal to 17.5 minus T lower in the y direction minus, what's my MG? So this tells me that my T lower in the y direction is equal to, so I have 17.5 minus 13.4, and I got that as 4.1 newtons. That's where that little 4.1 comes from. So now I could actually figure out what the tension in the lower string is, because if I look at this lower string here, something that I'm noticing is that my angle right inside there, that is a 30-degree angle. So T lower in the y direction would be equal to T lower sine 30. So this is 4.1 is equal to T lower sine 30. So that tells me that T lower is equal to 8.2 newtons. Now again, I'm using G is equal to 10 here, so if you're getting something else, it should be in the 8 range though, probably somewhere between 8 and 9. So that's how to get the T lower. The next question is, what is the magnitude of the net force acting on the ball? Well, what I like about this is that the up and down forces have balanced, but the horizontal force, that is the net force. So if I write this, okay, so if I do the F net, it's in the x direction. Well, what are my forces in the x direction? It's T upper in the x direction plus T lower in the x direction. Now, they're both to the left, right? They're both to the left, but they're in the same direction, so I'm going to add them. So, to calculate that, this is going to be T upper cosine 30, because that's the adjacent side, plus, sorry, I got to slide down here, T lower cosine 30 also, because the x direction is the adjacent one there. So I just pulled this out so I could do the math a little bit easier. T upper is 35, T lower is 8.2, and then this is cosine 30. Got my handy dandy calculator. So I got 40.2 newtons as the net unbalanced force. Now, next question is, what is the speed of the ball? Well, what do I know about the net force? If you're in circular motion, it's equal to mv squared over r. This brings up an interesting question. What is the r value? Well, if I come back over here and I look, the r value should be right there. So we're going to have to actually do a little bit of geometry. We're going to have to actually do a little bit of geometry. I will do it over here. So I have so this is the 1.7. This is half of 1.7. .85, because that's this distance here. It's half. And then this is going to be your radius. Now, you also knew this angle, so you could use the sine or cosine, or you could use the tangent to find it, or you could just use Pythagorean theorem. Oh, it's so interesting. So this is So I'm going to plug and chug here. So the net force is 40.2. The mass is 1.34. Speed is what we're solving for. I'm going to divide by, oh, R can't be 2. I'm sorry, I must have made a mistake. Clearly. Sorry. R is equal to 1.47. Yeah, the leg can't be longer than the hypotenuse. So I got speed is equal to 6.6 meters per second. And then the last part says, what is the direction of the net force? And because it's in circular motion, the net force, in this case it's left, but it's always inward. Okay, that was hard. Let's do this last one. So, oh, looks like there's a couple more. 77. It says, what is the terminal velocity of a terminal speed of a 6 kilogram spherical ball? So m is equal to 6 kilograms. Has a radius of 3 centimeters. And a drag coefficient of 1.6. The density of air is 1.2. This one seems like a plug and chug with one little hiccup. So I know that if it's falling at terminal velocity, the thing that's important is that it's at terminal velocity, right? Which means that the acceleration is equal to 0, therefore the net force is equal to 0, and therefore the drag is equal to the weight. I can buy that. Well, according to the textbook, the drag force is equal to 1/2 c rho a v squared. So if I set these two things equal to each other, so this is the drag and this is the drag, so I end up with mg is equal to 1/2 c rho a v squared. And you know these things. So it's a 6 kilogram ball. Gravitational field strength is 10. 1/2 c, which they told us is 1.6. Rho, they told us is 1.2. Now, here's the A thing. So the A is the only hard part. So there's the R. So the cross-sectional area, the effective cross-sectional area, is a circle. I mean, I know in a technical sense, you're seeing more area, but that's the shape of the object goes into the C. So we're going to go with pi r squared. But we are in meters, so 0.03 squared. So this is a small number. And then v squared. So let's just plug and chug in and see if we can do that. plug and chug that, and don't forget to take the square root, and I have 149. That's meters per second. Again, if you're using a G value of 10, I'm using 10. If you're using 9.8, you're going to get something slightly different, but it should be close. Okay, one more. 87 says, a car weighing 107 kilonewtons. Okay, so that's the weight. So basically it says that mg is equal to 10.7 kilonewtons. So it's 10.7 thousand newtons. Now, I just made it, so it's 10.7 kilonewtons, so it's 10,700 newtons. And it's traveling with a speed of 13.4 meters per second. Try to take an unbanked curve of radius 61 meters. So it says, what is the magnitude of the frictional forces required to keep the car on a circular path? All right, well, let's draw a force diagram, see what it looks like. So here we go. So there's the weight. It's on a flat surface. So there's the normal force. And then it's turning this way, so it has to have some force inward, and that is the friction. If you've ever tried to take a turn without friction, you just go straight. So this looks pretty good to me. So when I look at the net force on this thing, the net force in the x direction is equal to, well, it's equal to ma, but it's mv squared over r because it's going in circular motion. What is that? How do you express the net force? Well, look, there's only one force in the x direction. That's the friction. So to answer the first part of the question, the friction is equal to mv squared over r. So if I plug and chug that, now again, they gave us mg. I'm going to divide by 10 to get this. So it's 1070 for the mass. The speed was 13.4. Don't forget to square it. And the radius was 61. Handy dandy calculator. So we got a frictional force value of 3150 newtons. Again, I use a G value of 10, you might get something slightly different. Okay. The next part of the question says, if the coefficient of static friction between the tires and the road is 0.35, is he successful at taking the curve? All right, well, what do we know about friction? The thing we know about the frictional force is it's equal to the coefficient of friction times the normal force. But in this case, if you notice, because the F net in the y direction is equal to 0, therefore the normal force is equal to the weight. So in this case only, this is mu mg. So I'm going to set this equal to this down here. So these are both friction. So mu mg is equal to 3150. Okay. Actually, let's not do that. Let's try something else here. So I think let's just calculate this friction and then compare it. That'll just be a little bit easier. So it says the coefficient of friction is 0.35. So 0.35, and then the mg value is 10700. So it says the frictional force that you get from the road is 3745 newtons. And if you notice here, you only need 3,100, and you can get 3,700, so yes. Yes, he makes the turn.